Thanks everyone for attending this session. Again, my name is Andrea Continella. I'll be talking about a couple of research works I've been involved in the domain of automated security testing for smart embedded devices, right? Even though we'll see they're not so smart about when it comes to security, at least. I guess it's no surprise in this venue. Before diving into the content of this presentation, let me quickly and briefly say something about myself. I'm an assistant professor at the University of Twente here in the Netherlands, so just east side of Amsterdam, couple of hours train. And I'm part of the SCS group, which stands for Semantics, Cybersecurity, and Services, so quite a long name. And we do, as the part of the name says, cybersecurity in our group. We mostly focus on two macro areas, data security. So there are colleagues that do things related to homomorphic encryption, multi-party computation, privacy-enhancing technologies, and so on. And then system security, which is the more practical and technical aspects of security that I like. And most of my research is focused on three main research lines. Malware analysis and defenses, threat detection and response, and automated security testing, which is what this talk is going to cover in the next 45 minutes. I'm also a huge fan of CDFs. That's how I got into security. So I started when I was at my bachelor in Italy, playing with the Tower of Hanoi team in Milan, that then got bigger in the Italian team, the Macaroni team, and then I joined Shellfish when I moved to the US in UCSB Santa Barbara. And nowadays we have an active team in Twente, the Twente Hacking Squad. And I had the luck to play CDFs, many CTFs around the world, mostly ending up in Vegas for DEF CON finals. You can see picture here. I guess this is DEF CON 2019. And this is actually during the actual competition. There are a few more pictures of what happens usually before the competition starts, where we start grabbing all kinds of snacks and energy drinks to survive and stay awake for practically 3 days. And eventually what happens next is that, well, after 3 days without sleeping, people start collapsing on the ground. All right, and now about myself, let's dive into the content of this presentation. So I'm going to tell you a little bit about my journey in the area of automated vulnerability research for smart embedded devices. We'll talk about some challenges that we need to face when analyzing and testing IoT devices, smart devices, and firmware in general. Then we'll cover black box fuzzing and our solutions and tools that we developed for these purposes, with a focus then on device firmware update as a critical operation for smart embedded devices, and then we'll conclude with some summaries and future directions. So I guess I don't have to convince anybody here about how popular IoT devices and smart devices are nowadays, right? At the same time, I'm still quite surprised about the crazy new devices that come out on the market. Things like smart toasters, smart lights, smart sockets are maybe now more or less standard, I would say. But then we also have devices like a smart egg minder. What the hell is this supposed to do, right? Why do we need these? I don't know, but for the law of economics, there must be people buying and using these devices. And anyway, what we found, again, no surprise, that most of these devices are vulnerable. And although their threat model might not be so dangerous when we think about their functionality, right? Nobody cares about hacking your eggs. We've seen attackers using these vulnerabilities at a larger scale, mostly to create botnets and to then perform, for instance, distributed denial of service attacks. That's what happened with Mirai. That was the most probably famous example when IoT malware infected hundreds of thousands of devices around the world, and then started performing a very large distributed denial of service attack that actually put down a couple of critical nodes on the internet. Now, one interesting aspect where we talk about vulnerabilities in this domain is that the types of vulnerabilities that we see are usually very old types of vulnerabilities. So things that the community has known for such a long time and for which attackers usually do not need any kind of sophisticated exploitation techniques. And in fact, the firmware running on these devices usually does not present many or all of the security mechanisms and mitigations that we're used to nowadays in modern operating systems. So things like address space layout randomization, control flow integrity, yeah, forget it in the IoT device domain. At the same time, firmware presents some differences, some significant difference when it's compared to traditional software applications. First of all, and mainly, firmware is hardware dependent and often relies on external peripherals that are usually managed by custom code. Firmware lives in unique and minimal environments, usually with non-standard or let's say weird configurations, hard-coded memory addresses, shared memory, and all these kind of things. Custom interrupt handlers, these are all things that are quite common in the firmware domain. And on top of this, firmware usually is implemented and developed and relies on different architectures. Sometimes these architectures are also proprietary ones. That makes it even more challenging for us to, as security analysts, to test this kind of firmware. So all these aspects make, again, security analysis particularly challenging. And if one wants to apply traditional security analysis and testing techniques in the firmware domain, well, as in the traditional software domain, we have two main areas. We can start with dynamic analysis. So we ideally can run our firmware images in an emulated or virtualized environment. Ideally, we can instrument it, we can run our coverage guided fuzzer and potentially find vulnerabilities. Well, not really, because dynamic analysis for firmware is, again, particularly challenging. And as of now, despite there have been quite a lot of research with interesting and promising results in this domain, we don't have a generic solution that is reliable enough. And this is, again, due to the fact that firmware is very much dependent on the hardware. So when you pull it away from the hardware, you miss all kinds of dependencies, and then you have to implement manually all these kind of custom and weird setups with custom interrupt handlers, with custom peripherals, with sometimes weird architectures, and this makes, again, modeling a dynamic analysis environment very, very challenging. The other option, of course, is that we can do static analysis. That does not have many of these limitations, but static analysis has the usual problems of often generating too many false positives. And this is particularly true in this domain because most of the times firmware is multi-binary. What does this mean? Most of firmware is actually Linux-based, somehow with a minimal or a minimized version of Linux, and comes basically in a squash file system. So when we get a firmware image and then we unpack it and we look at it, what we get inside is an entire file system, and within this file system we have often hundreds of executable binaries within it that somehow are connected or interact with each other to implement the firmware functionality. For this, we developed a tool a few years ago that applies static analysis by finding the connection between different executables and then applying what we call multi-binary intent analysis to identify vulnerabilities. And then we show that this actually effectively reduced the number of false positives. I'm not going to talk in detail about this work in this presentation. I'm going to just leave a reference in case some of you are interested. There is a research paper online. Also, the source code of the tool is available on GitHub in case anybody wants to check it out. I'm not going to talk to this because there is also a more fundamental problem and more generic limitations that affect both static and dynamic analysis. And that's the fact that both types of analysis, by definition, require a firmware image to analyze. But unfortunately, in the IoT domain, on the smart embedded domain, this is not often easy, because vendors do not often publish the images online, and it can be feasible to recover firmware images from the devices or from the network connection, but this is not always trivial. Sometimes it requires quite a lot of effort in manual reverse engineering, also on the hardware side of the devices, and this is often not scalable. So what do we do when we don't have the firmware image, but we want to test a specific embedded device? Well, in this case, the only viable solution is black box fuzzing. I'm not sure how many of you are familiar with fuzzing, but on a high level, what we do is that we get a target IoT device, and then we start generating some inputs that we send to the IoT devices, and we hope or pray that these inputs somehow trigger a vulnerability on the target device. So if we see an example, let's assume here that this is a portion of the corresponding source code of the firmware running on this embedded device. And we can see here that this firmware image reads 500 bytes from a network socket, and then this data is copied into another buffer that is only 100 bytes. So here we have a buffer overflow. This might seem, a kind of a trivial or stupid vulnerability, but it's actually, what happens very often in the firmware domain. So what we do here is that we start our fuzzer, and we start generating inputs that we send to the target device. And let's say we start generating a bunch of A's, then we generate more A's, and then at some point, if you're lucky, we generate a message that is long enough to trigger actually the vulnerability in the target device so that we can recognize it. In practice, this is not so easy, and the main reason is that devices usually, as a first step after receiving data, implement some function validations. So what they do is they check if the input that they receive comes in the expected format, and if not, the input is immediately discarded. So in this case, we see that this device is accepting an HTTP request. And if we send just a bunch of A's that are not packaged in the HTTP format, well, this input will be immediately discarded, and then we will never trigger the vulnerability that happens later on in the code. So the main issue here is that black box fuzzing, as it is in the naive way, is not able to generate inputs in the right format that go deep in the code. And remember that here we have the example where we have the source code, right? But we don't have the firmware image, so we don't know what kind of protocols or format the device expects. And in the IoT domain, there is such a variety of protocols and custom things that we cannot make any assumption on what kind of format we need to produce. So what we can do is that there has been another research by other researchers a few years ago that proposed a different option, which is smarter than applying only black box fuzzing. And that consists in leveraging the companion apps. So usually IoT devices come with these mobile apps that you can use to interact with the devices. And by definition, these apps know how to talk to the device, right? Because they implement this functionality. So the assumption and the idea here is that they contain the logic within the application code to actually package the data in the right format for the IoT devices. So the idea for this is that, okay, let's instead, when we generate and produce our fuzzing inputs, instead of throwing them directly to the device, let's feed the mobile apps. Right? So in our previous example, ideally we start generating our bunch of A's, we give them to our mobile applications, and then the mobile applications ideally push them already in the right format because they know how to talk to the device. Again, if this is true, very nice, we can find the vulnerability in this example. This is way more effective than using black box fuzzing, but still as a main issue. And it is when we send these inputs to our mobile apps, the mobile application itself now can implement some kind of sanitization and validation of the input. So they can constrain what kind of inputs we can provide and what gets filtered in the mobile stage. Let me actually give you a little bit more example first on this current work that is called the IoT fuzzer. That's the fuzzer that I mentioned that uses this approach. And what they do basically in their implementation is finding in these mobile applications UI elements that lead to generating network traffic. And then they fuzz the functional arguments of these UI elements. So let's see an example. Here we have a function that receives a value from the UI. And this value is used to set a brightness level, probably somewhere in a camera or whatever on the IoT side. And this value is then passed to another function, encoded, and sent to the device. So what IoT fuzzer does is finding these elements at the UI level and starts fuzzing these values here. So this value here at runtime would be changed and would contain our bunch of A's. As a result of this bunch of A's end up here, end up here, end up in the encoding function, and so they're packaged in the right format for the IoT device. Again, very nice, very smart. There is still one issue. The issue is that what happens, not in the example we'll see another later, usually in the mobile applications, is that the data that they receive from the UI goes actually through two steps. The first step is input sanitization, and only later, when the input is sanitized, formatted, and stored in internal data structure, then this input is then serialized over the network and sent to the IoT devices. So we can see an example from actually real-world apps that we found in our experiments. In this case, there is an application that is reading the admin password from the UI. So the user sets this password, and then there are a bunch of checks that verify whether this password contains special characters or if it is longer than a certain amount of bytes. And only if these conditions are true, so if the password does not contain special characters and is shorter than 32 bytes, only in this case, the message is sent to the IoT device. So if we just, in our case, provide a bunch of A's and then we want to send 200, well, this is going to be filtered by the application. It's not going to be sent to the device. Only later, only after this sanitization is implemented, then the applications package the data in the right format. So we see here again, there's kind of a custom format with a JSON file, which is encoded in base64 and then is sent through a HTTP request. So now we have two solutions that have both limitations. One is we can just ignore the apps. We send inputs in a very naive way. But then the problem is that these inputs, most of them will be invalid, so will not trigger any vulnerability in the depth code, deep code in the device. On the other side, we have what IoT fuzzer does, so fuzzing at the UI level of the mobile application, which is better, gives us valid inputs, but is limited by the sanitization that the application implements. And what we did in our research is implementing a tool that automatically finds the sweet spot in between these two areas. So we designed a fuzzer that automatically finds functions in between these two, these two functionalities that produce valid inputs and are not limited by the upside sanitization phase. We call this function fuzzing triggers, and we called our own tool Diane. So fuzzing triggers, again, are these functions that are in between upside validation and data encoding. So in the control flow, in the execution of the application, they are executed after sanitization, but before encoding. And to find automatically these functions, Diane, so our fuzzer, takes as input, as we mentioned, a companion app. Then it constructs a call graph of the application. So this is a graph that connects all the functions in the APK. We mostly focus on Android, and basically contains an edge when there is a function A that calls function B. In this graph, we first apply static analysis, and we identify what we call candidate send message functions. These are functions within the application that potentially send a message, as the name says, over the network to the IoT device. We then use dynamic analysis to validate these functions. So we run the application and we check whether the findings from the static analysis are actually correct. So we find a validated send message function. And then we use a hybrid analysis of both static and dynamic. We'll see it a little bit more in a few slides. Basically, where we move upward, right? So in this approach, our candidates send message are at the bottom of our graph, of our call graph, and what we want to do here is going up. So we go for all the potential path. We go up toward the UI, and when we go up, we check whether any of the functions that we find are potentially encoding functions. Where we stop seeing encoding functions, or whether the last function encoding function that we found, then we stop there, and we know that this, is the best place we can use for fuzzing, because it includes all the encoding functions that are executed afterwards, but do not include all the functions that are executed before that likely contain sanitization. We can zoom in a little bit into this step. So we use this bottom-up approach, where we first identify these send message functions. Then what we do is that we perform a backward slice upward to the UI. So basically what we do is that we find all the execution paths from these send message functions that go up toward the UI. So toward the functions that implement reading operations from the data that is placed from the UI. And once we do that, we collect all the functions that are traversed in all these execution paths from the bottom to the UI. And then for each of them, we run our application, we instrument the functions, and we check on their entropy. So mostly what we do is checking what kind of entropy they introduce on their output variables. So every function has some kind of inputs and some kind of outputs. They could be return values. They could be field in a class, in an object that they are setting. We have a couple of heuristics to find all these inputs and outputs. And then we compare the values that we see in output and the values that we see in input. And we check whether the output values have significantly more entropy than the input values. That's a signal of encoding, of some kind of data transforming, that's what we call them. There is another research that showed that there is a specific threshold that you can use for identifying when a function is an encoding function, depending on how much entropy they introduce. So we leverage this research, and we use this to identify encoding functions. And then what we do finally is that we identify these fuzzing triggers, so this sweet spot that we want to fuzz, as the data transforming functions that are not dominated by other data transforming functions. Here we use a definition that comes from graph theory for the domination, but basically, in basic word, what this means is that we look at the functions that are more on top, right? So the functions that are higher in the call graph. So basically, the first encoding function that we see from when coming from the UI. Let's see an example on actually a simplified source code of an app that we analyze in our experiments. In this example, we see this function here on the bottom, send to device. This is what we find as a send message. So this is a function that eventually you provide them some bytes, and then it's going to send these bytes to the IoT device. If we start from here and we go upward, so we do a backward slice to see who calls this function and how this function is used, we see that this function is called in this other function, and the argument is actually the return value of another function, encode. So we go up again and we check what this encode does. This encode function and the return value, which is not shown here, comes from this argument again, string s, and this is, if we see on the bottom again, this means that this is this name variable, which is the parameter of the set device internal function. Then again, we go up and we say, okay, who uses this function? Another function on top, which is the set device name, which is actually our end stop point here, because it is at the UI level. And we see that this value name here goes through a couple of steps that also apply some kind of sanitization, where there is a substring, and eventually this again goes back to the UI. So now we have these links and slice of values that are being used and propagated from the UI to our send message function. We do execute these functions dynamically, and then let's assume here that we identify that that's actually what happens in our experiments. This function here is the only one that shows a significant entropy in their output variables. What this means is that this is our, in this case, fuzzing trigger, as this is the only function that introduces a certain amount of entropy. This is the only encoding function in this example. So that's what we use as a fuzzing trigger. So this is the function that when we run the application, we want to stop here and we want to mutate its input variables to produce some outputs for the IoT devices that potentially and hopefully are more effective in triggering vulnerabilities. The implementation of our tool, which is shown in this slide, basically we use Frida for instrumenting Android applications. We used another tool to record, it's called Rerun, to record and replicate interactions with the applications. You might wonder, when we analyze the Android application, we need to click on something to actually explore the functionality. We do this by recording the interaction the first time manually, and then replaying the interaction for all the subsequent runs. So we run our companion apps, and when they at runtime execute our fuzzing triggers, what we identified as fuzzing triggers, what we do is, we start mutating all the input parameters. In this example, the argument to this function. We try our mutations, in this example, our bunch of A's, and this eventually results into requests for the IoT devices that potentially and ideally trigger vulnerabilities. So now the question is, how do we find whether we triggered any vulnerabilities? Remember, we don't have any firmware, right? So how do we know whether there is something that touched a vulnerability? So what we do is that we monitor the response from the devices. We apply a couple of heuristics. So we check first, if the device stops responding, or if the device maybe responds in a weird way with some error messages, or with some very short response that is not in line with what we observed during the normal testing. And what we also do is that we use a separate device, a separate smartphone, to check on the state of the device. So we can identify when the device stops working. We test this, so we use our tool Diane to fuzz 11 IoT devices from different brands and categories. We found that 7 out of 11 apps for these devices did contain input sanitization. So where our approach was indeed necessary for generating good fuzzing inputs. And on a larger scale, we found that roughly 50% or 51% of companion apps indeed use sanitization before sending data to the IoT devices. For these 11 devices that we looked at, our tool Diane identified 54 fuzzing triggers with 5 false positive, and 5 times in which the fuzzing triggers were the same as our send message functions, which means in these 5 cases, they were all related to a single one app. There was no encoding, right? So there was an example when the application did not use any encoding at all. Very good. So we compared our results to IoT Fuzzer, which is this fuzzer that I showed initially that uses companion apps but only stays at the UI level. And as you can see here, we did find significantly more vulnerabilities, a few more 0 days, and we did find indeed that many of the vulnerabilities that we found could not be identified by IoT Fuzzer because they require some inputs that get sanitized by the mobile applications. So that's again showing the necessity of using a tool like ours. I'll show you a quick example on what happened when we fuzz a popular smart lock. Let's see if the sound works. Okay, so this happened during, does anybody recognize this or can tell what this is? So we didn't know. So when we started fuzzing and experimenting with this device, that we started hearing this sound. So what the hell is happening? And then somebody else entered in the lab and recognized this SOS in Morse code. So what happened then by investigating this case and contacting also the vendors, so we disclosed all the vulnerabilities that we found to the vendors, is that our fuzzing actually managed to overwrite a pointer within the firmware of the device, and that let the device enter in an error handling state that basically beeps SOS in Morse code. So that was surprising, but likely somebody in the lab, recognized this pattern, because I wouldn't. Okay, so if you want to read more about this, there is again a research paper that we published. There is also the code is again on GitHub, so public available. Now, what I also wanted to quickly mention is another recent work in this direction to further show the capabilities of this kind of approach. And in fact, we then asked ourselves, can we apply this same approach to more hidden targets? So if you have a Google Pixel device, I do, it's a recent one, your smartphone comes with a separate coprocessor. It is called Titan M, which implements a trusted execution environment. So a trusted execution environment is an isolated environment that runs a separate operating system where the most critical security operations are actually executed. So in a Google Pixel, recent Pixel device, when you, for instance, unlock your device with your finger, the actual fingerprints and the verification of the fingerprints happen in this additional coprocessor that implements, again, a different operating system. It's called the secure world, and interact with the non-secure world, which is basically the Android kernel. So what we did here is that we use a similar approach as we did with companion apps. And instead of looking at firmware, we look at, okay, who does the firmware talk to? The Android kernel. So let's look at the Android kernel. And what we did is that we find the right places in the Android kernel to instrument, to communicate with this chip, and we implemented our fuzzer within the Android kernel. So we practically moved and made the Android kernel a fuzzer for this chip. And, well, surprise or not, we did find vulnerabilities in the Google Titan M super secure chip as well. Some of them, the one that you see on the top table, were actually known to Google. So were known vulnerabilities. We use this as a way to validate our fuzzer. But we also did find two unknown bugs that you see here on the bottom. They turn out to be not so severe, so they could not be used to, for instance, get remote code execution or similar. They could only cause the chip to halt, so you could do some kind of denial of service attack, but not really something too critical. But the interesting here to notice here is how quickly we can find these vulnerabilities. If you look at the average number of messages that we need to generate to trigger these vulnerabilities, is very low, right? In many cases, less than 100 messages, which means that for most of these vulnerabilities, we could find them in 2-3 minutes. Which shows again, the capabilities of these approaches, of these fuzzing techniques, when you know the format and you know what kind of data you have to send to your target. Again, if you want to read more, there is a research paper online. Also, of course, feel free to ask me around if you have other questions. And finally, last thing I wanted to tell you for this presentation, more recently we started looking at another critical security operation for smart embedded devices, which is their firmware update mechanism. And we did study the firmware update mechanism for a few devices, and we find out that the mobile apps, especially for these new IoT devices, again play a critical role. So what happens often nowadays for IoT device firmware updates is that this mechanism is triggered and mediated by mobile apps. So usually, of course, every vendor and every device might have slightly different implementation of this scheme that they're showing, but there are a couple of steps that are always common and that we found basically in all the devices and apps that we look at. So first of all, what happens is that usually the mobile app is used to check the firmware version that is running on the target device. This can be triggered by the user. It can be done automatically, depends, but that's a common step. And of course, this can happen by, for the app to directly communicate with the device, or this communication could go through the cloud. It depends, but on a high level, same step. Second thing, the device, in this case, sorry, the application gets the latest firmware version if this is necessary. So if the device is not running the latest one. Again, this can go through the cloud. It can be a direct communication. In some cases, we have seen firmware images embedded within the APKs, which to me does not make a lot of sense, also because then that means that you have to basically upgrade the mobile app whenever there is an upgrade also for the firmware image. Again, multiple ways to implement this, but same high-level concept. You get the latest firmware image, and then finally you transfer this image to the device and you make it run. So far, so good, right? Of course, things can go terribly bad when devices do not properly implement integrity and authenticity of the firmware image that they receive. If there is no signature verification on the firmware side, or if this verification is weak or vulnerable, then this means that attackers might potentially do bad things. And in fact, apps, network, and cloud servers, all these things are involved in this scheme, might be potentially compromised. Or we might have scenarios like if you think at Airbnb scenario when the guest has an app to interact with the device that are present in the smart house, in the guest house. In these cases, the apps are not trusted, right? They're being run by potentially malicious people. So what happens is that when these apps are compromised, or the networks are compromised or malicious, and the firmware images do not implement proper verification and integrity check, we could end up in things like device breaking. Maybe there is just not a proper error handling of this firmware update. So if we messed up something, then the device doesn't boot anymore. We could end up in doing firmware downgrades. Maybe there is some kind of firmware verification on the IoT sides, but this verification does not take into account the fact that the firmware that is being received is the latest one, which means that you can potentially downgrade to a previous versions that maybe contains already some known vulnerabilities. Or in the worst case, there is no verification at all, so you can do whatever you want. Just send your own code. I'll execute it for you. Thanks very much. So we did study the state of this and the security of these firmware updates mechanisms, and we started with the intuition that most of the times in these companion apps, these firmware updates mechanisms are implemented by SDKs. So there are libraries that are more or less shared across vendors and devices that the developers use to implement these functionalities. So we started by collecting a couple of popular devices from the Amazon bestsellers categories and popular IoT SDKs. We got our dataset and we started reverse engineering them. After a quite intense, sometimes painful process, we also started performing some dynamic testing. So we found by reverse engineering that some of these SDKs were vulnerable and were not implementing the update mechanism in a secure way. So we tested it dynamically, concretely on a few devices, and we also created fingerprints of this SDK. The idea to use fingerprints for these SDKs, for this vulnerable SDK, is that now we can use them for a large-scale analysis. So we can check on how many companion apps and how many devices potentially use or rely on SDKs that are vulnerable. So we focused initially on 23 devices with companion apps from 16 bestseller categories in Amazon, and we did find 6 vulnerable SDKs that have some kind of vulnerabilities in the 3 different classes that I mentioned before. We generated fingerprints for this, and then we use them to study how spread these issues are, using a data set of almost 40,000 IoT companion apps in Android that come from the Google Play Store. Out of these sets, more than 1,000, so 1,356 apps that are currently on the Google Play Store use at least one of the 6 vulnerable SDKs that we found. And most of them are vulnerable to modification attacks. So basically, you can do whatever you want. This means that potentially you can also do breaking or downgrading, but of course that's less interesting from an attacker perspective. And then one app was only vulnerable to the breaking attack, so you can basically perform a denial of service, but you cannot execute your own codes. And for one app, 8 apps, they were only vulnerable to downgrade attacks. So you can replace the running firmware with a previous version that potentially contains known vulnerabilities. And we did find also that among these apps, 24 apps are actually used to control 61 devices that are in the top 50 bestseller category. So again, these apps and these devices are being used in practice. They are quite popular, and most of them, they come with, not most, but a significant portion of them, they come with SDKs that are vulnerable in terms of management for the firmware update mechanism. Again, research paper, if you want to read more, this is going to be presented at the Euro SMP conference in a few months in depth. So again, nearby. And with these, I'm almost done. Some conclusions from this talk and from my, let's say, journey in this area. First of all, I think my main message and what the main lesson that I learned over this year is that embedded devices require us to rethink our automated security analysis. So we cannot simply apply things that we've been doing for software as it is for firmware or devices, because this doesn't work. When we do this, when we rethink these methodologies, these techniques, I believe that understanding and modeling the interactions of the firmware running of these devices is critical. And at the same time, I feel that nowadays, with our research, with research also from other people in the community, we have finally some quite decent tools for identifying vulnerabilities. Right? So we are doing much better. We have more reliable tools. We find vulnerabilities in these devices. So now the question is, okay, we do find vulnerabilities, but how can we automatically now prevent them or patch them once we find them? Those are all questions for ongoing or future research. There are a couple of things that we are already investigating at the University of Twente. First, for instance, how can we inject patches in firmware images by applying static rewriting? And this is, again, there have been tons of approaches for static rewriting for Windows, Linux binaries. None of them work with firmware. This presents fundamental challenges, so we need to rethink and rechange our techniques for static rewriting to apply patches. We're also looking at how to identify and isolate components into monolithic firmware images, which are basically these blobs, these kind of firmware images that do not come with any operating system. There is no abstraction between data and code. There is just a mix of bytes, and you have to figure out what's inside. We are also building in Twente a living IoT lab. So there will be a nice room full of IoT devices where students, researchers, and employees can do research, and they can also use for their own things. And we're also looking at how to design and develop tools to perform anomaly detections on these devices with the main constraint, again, that traditional approaches do not work, because now and then if we move into the IoT devices and the smart devices environment, we have so much little computational power that all the existing tools and approaches do not work. So we need to think about something more smart or more lightweight for these environments. We are also hiring basically all levels, so PhDs, researchers, professors. So if anybody is interested in this kind of research, feel free to have a look at the website or send me a message. With this, I conclude my talk. Thanks a lot for attending, and I'd be happy to take questions.
Any questions from the audience?
Hey, thanks so much for the really interesting talk. I have a few questions.
Yeah.
Okay, so first of all, technical one. If the sanitization is in line in the functions that prepare the packet to be sent out, then this technique won't catch them, right?
Yeah. So that's true. Let's say in the worst case, when this happens, at the same line function that is, let's say, our encoding, let's say, function, then we basically fall back to the same approach as IoT fuzzer, right? So we cannot do worse than them, than the existing tools. In the worst case, we do basically the same, but that's true. Another limitation is that sometimes it could be possible, we haven't checked that some of these things are implemented in the application in native code. We only look at Android application on the Java Kotlin side, but potentially apps might use native libraries for some of these steps.
Right. Are you able to apply the same techniques to native libraries, or is it a matter of engineering, or is there a fundamental limitation?
I think it's a matter of mostly engineering. I would expect that when we construct this call graph and apply our backward slice, there will be more false positives because handling binaries, and the loss of semantics you have in binaries is not the same as in Java. With the Dalvik bytecode, we can get something, we have pretty much complete information and types that we don't have in the binary side. So it's a matter of engineering plus dealing with more false positives. That's what I'm feeling.
Right. Okay. Thanks so much. Okay, and a couple more. So, do you have any work for on the iOS side, or is it just you're looking at the Android apps?
So for this research line, mostly on Android, we started looking at iOS as well recently. So far, not in the context of let's say IoT, not for applying these approaches on iOS, but we are also looking at iOS in terms of comparison with Android in terms of security features, but not looking at the devices.
Okay. Will this approach be applicable to iOS, or is it are there like big differences between the platforms that make it difficult to transfer?
Yeah. No, so I'm thinking of all the steps we do and whether I see easy mapping for all of them. Static analysis, definitely yes. Dynamic analysis, free the runs as well. So I think most of it can be done as well. It's again a matter of engineering, but in that case, I would say it's a matter of massive engineering. Because being iOS closed source, we are working on it right now on other things. The amount of work is significantly higher. But on a high level, you can apply the same thing.
Cool. All right. Last one is okay. So just now you showed that of the top 50 apps, half of them use the compromised SDKs, but then of all apps, only a much smaller fraction use them. So why is that the case?
Say it again. Sorry, I couldn't.
So just now you showed that amongst the top 50 apps, half of them use vulnerable SDKs. Mm-hmm. But then amongst all apps, a much smaller fraction use them. But so why is that the case? Why do the top 50 apps, why are they more likely to use vulnerable SDKs?
Yeah, so when we look, we didn't look at the top 50 apps. I think you mentioned here. We look at the top IoT SDKs, initially as an input, that were already shared across many apps. So not only the top 50. The percentages, as you mentioned, is not even close to 50%, or it's a very lower ratio. But I think what is interesting here is that we see within this set of apps very popular ones, right? So apps that are targeting very popular devices. And this is not necessarily, that these 24 apps are in the top 50 in Google Play Store. Is that the devices they control is in the top 50 of Amazon bestsellers.
Right. Okay. I see. But so why are those apps more likely to have this vulnerability? Is that do you know why? Or
I don't know why, to be honest. Okay. I think so. I know that one of these vulnerable SDK that we found is a very popular one. and I guess it's being used by many popular devices. The positive thing is that this vendor was, the one that reacted to us more quickly, so they already fixed their SDK, which is good. But yeah, I don't have a precise answer. Yeah.
Great. All right. Thanks so much.
Thanks.
Well, thank you very much for the awesome talk. Seeing the time, we can't take any more questions. If you have any more questions, feel free to meet up. Thank you very much.
Thanks.